We're now going to do a quick study of probably the one antiderivative that has the most wrinkles in it, the simple antiderivative with the most wrinkles. And that's where our function is 1 over x. Let's take a quick look at that in context. Oops. Let's get a straight line here. There we go. And we remember the graph of 1 over x has that nice vertical asymptote, and then a horizontal asymptote, and the same thing on the negative side, like so. That's the graph of y equals 1 over x, and here's x. Now, we're interested in the integral from -3 to -1, so those are x values. -1 to -3. So, we should put quotes around the area here. This integral would be negative because the function lies below the x-axis, but it's a perfectly reasonable integral there. So, yeah, we should just be able to go ahead. Now that we have visualized what this integral represents, and we know that there's an antiderivative of 1 over x, we should be good to go. All right, so what do we need here? Well, we have the integral from -3 to -1 of 1 over x dx is equal to, well, this is our little f here, and if we anti-differentiate, or take the antiderivative, we should get ln of x, because if we differentiate ln of x, we get 1 over x. We're going to evaluate that at x equals -1 and -3. And there we hit our first and major hurdle in this problem. Ln of -1, that's undefined. Uh-oh. And yet, there's nothing wrong with what the integral means. We can look at that, and it looks perfectly reasonable. It's negative, but negative values and integrals are fine. So we also have that the derivative of ln is 1 over x. Where does this problem come in from? Well, the problem's a domain issue. This ln of x is defined only for positive values of x. However, 1 over x is defined for, 1 over x is defined for all x's except x equals 0, of course. So we have a disconnect between these domains. Now, we could do some fun proofs with this. It turns out it's not complicated, but I think I'd rather just jump straight to the answer. The most general antiderivative of 1 over x is not going to be ln of x, it's going to be ln of the absolute value of x. Once we put that absolute value in, all of our question marks go away. We have the ln of the absolute value of -1. And then we have the ln of the absolute value of -3. And that is perfectly reasonable. We get -1, -3, we're all good there. And then we get ln of +1 after the absolute value minus ln of 3. And that value turns out to be around -1.0986. Ln of 1 is 0, ln of 3 is positive, but there's a negative out front. And this is negative, and that's good, because from our area sketch we expected that. Now, I think this pulling of absolute values out seems maybe a little bit magical. The proof isn't hard, but it's easier to think, I think, to get a graphical perspective on it. Let's go back to what we know about relationships between graphs of functions and the graphs of their derivatives. The ln of the absolute value of x is exactly the same as ln of x when x is positive. We get that nice vertical asymptote and then the slow growth as x gets bigger. When we put the absolute values around x, we can start putting in negative values. And we imagine, well, what's the ln of -1 absolute value? Well, it's the same as ln of 1. So there's a symmetry. We actually get this positive branch of ln of x copied over to the negative side. And then we ask, what if we take the derivative? If we do that, then the slopes on this graph turn into the values on this graph. All right, let's look at the positive side here, positive x values. These slopes are all positive. They're positive and very, very large when x is close to the axis here. And then they're positive and smaller and smaller. What do we get? Positive values that stay positive but get smaller and smaller and smaller. Hey, that looks like 1 over x. On this side, all the slopes are negative and getting bigger and bigger and bigger. The slopes are negative and small negative, and then getting bigger and bigger and bigger negative. And we can infer that if the derivative of ln of x on this side is 1 over x, then the ln of the absolute value of x on this side is also going to give us the graph of y equals 1 over x. Now this is not at all the first guess anyone would make, but it does seem fairly natural that there's some kind of symmetry here, and the absolute value is exactly the kind of symmetry, it turns out, that we need to have. The derivative of ln of absolute value of x is 1 over x with no absolute values. 1 over x is fine everywhere. The only reason we need the absolute values is because ln is only defined for positive x values. So with that being said, you should definitely go back to your table earlier on where we said what's the antiderivative of 1 over x. We're going to consistently use the absolute value of x, ln of the absolute value, plus a constant, when we do this table entry moving forward.